Hello, welcome back to the course on polymeric biomaterials. We are still looking at bulk, behavior and responses, and as part of this theme, in the previous lecture, lecture number 24, we started looking at the concept of viscoelasticity in polymeric biomaterials, and we spent quite a bit of time in the previous lecture looking at different manifestations or aspects of viscoelasticity, including creep, stress relaxation, hysteresis and so on. In this lecture, what we want to be able to do is to turn our attention to looking at some linear viscoelastic models as a means to capture some of the physics of viscoelastic manifestations mathematically. So with that broad goal in mind, in today's lecture what we will be doing is offering some comments initially on what it means to be looking at linear viscoelastic models, and we have hinted at this, at what linear viscoelasticity is in the previous lecture as well. And then we will try to see how to think about physically the elastic and the viscous components and what are the equations that govern them, and then try to see how they can be combined in some form or fashion across two different models, namely the Maxwell and the Kelvin-Voigt model, and we will see then if the model equations can help us predict our familiar manifestations of creep and stress relaxation, and we will see which model predicts what better and where a particular model actually fails to predict a particular process or a phenomenon. And then towards the end we will offer some very brief comments on other models that can overcome some of the limitations associated with Maxwell and Kelvin-Voigt, and then we will wrap up this lecture with again looping it all back to viscoelasticity in the context of tissues and polymeric biomaterials, with the particular example of the articular cartilage. So with that, let's jump right into today's lecture by first recapping the key aspects of viscoelastic responses in polymeric biomaterials, namely two aspects that are of relevance to us in today's lecture: creep and stress relaxation. Now creep essentially is a constant stress is applied and the strain is tracked over time. So this is the application of a constant stress, and the response of a polymeric material could look like this, right, where initially there is a higher rate of increase of strain with time, and then with time the rate of increase of strain sort of keeps decreasing, eventually perhaps reaching a constant value, or in some cases it could continue to increase at a linear rate, although at very small values, right. So those are some typical responses that could be associated with different types of polymeric biomaterials, depending on what type of material you are talking about, right, thermosets versus thermoplastics, what is the Tg in relation to the operating temperature. All of these factors will determine the exact nature of the creep response. But this is one classic textbook example. Of course, relaxation is where a constant strain is applied and then the stress in the material is tracked over time. So that is this constant strain applied, deformation applied to the material, and it is held, and the stress relaxes over time, and this is again one sample where the stress continues to decrease with time, and in some cases the stress for very long times can end up going very close to zero, or in some cases again, depending on the polymer you are talking about, you might end up with residual stresses. Again, remember, these are both in both of these cases, both creep and relaxation, the load that is applied or the stress that is applied in creep and the constant strain that is applied in stress relaxation, both of them do not change with time. Once you apply the constant stress in creep or the constant strain in relaxation, you hold it there, right, and then you study as a function of time how does strain change as a function of time for creep, and how does stress relax as a function of time in stress relaxation. Again, this is just a snapshot we are showing here. We have dealt with this in far more detail in lecture number 24, where we have looked at creep, retardation, creep compliance, stress relaxation and relaxation modulus. So, if you have not looked at that lecture yet, now would be a time to go back and look at that lecture first before you look at this particular lecture. Because our goal here is to develop models to be able to capture the physics of creep and stress relaxation. Essentially asking, can we use mathematical equations, fairly simple mathematical equations that can help us predict, at least qualitatively to some extent, the responses associated with creep and relaxation for polymers. So, with that background, we will first offer a few comments on the assumptions we are making. We first note that all of this that we are talking about applies to what you would call linear viscoelasticity. So, all of this are what you would call assumptions of linear viscoelasticity, where we are talking largely about very small loads or deformations, and this which is simply saying that the total strain due to multiple loads can be thought of as a sum of strains caused by each load individually. This is called the superposition principle. And when you are dealing with linear viscoelasticity, this assumption applies. And that also means that for these kinds of models, the stress strain relations can be written using a sum of linear spring and Dashpot elements. So, we have introduced two new words here, spring and Dashpot, and we will see in just a bit what they represent and how they can help us model different aspects of viscoelasticity. Now, why is it this important to look at? Any model is only as good as its assumptions in some sense. So, when the assumptions get violated, the model predictions will no longer be meaningful. So, it is very critical when you do modeling to first ask what are the assumptions you are making. We have listed some key assumptions that are relevant for us to look at linear viscoelasticity from the purposes of simple models. Now, let us take a look at what the spring and Dashpot elements are. Now, we have already seen that viscoelasticity can have at least two. If you break it down into two words, you can have two different aspects contributing. One is the elastic component, the other is the viscous component. The elastic Hookean element, as we have seen earlier, the elastic solid here is modeled as an idealized spring. So, this is an ideal spring which is governed by Hooke's law, where essentially stress is proportional to strain, and E capital E is simply the modulus of elasticity. And the viscous component or the viscous Newtonian element is modeled using a Dashpot, essentially a piston with a purely viscous fluid inside, a shock absorber, if you want to think about it that way, as shown here. And in this case, it is governed by Newton's law, where the strain or the deformation itself is not critical here. What really matters is the rate of deformation. So, stress is proportional to the strain rate or rate of deformation, and that is what is given by Newton's law here. Sometimes you might see this law also written as tau is equal to eta times d gamma over dt, or tau is equal to eta times gamma dot. Again, this nomenclature is typically used if you are using shear. This nomenclature is used if you are using tensile or compressive. The other aspect, of course, this is simply the nomenclature for strain rate. The other aspect to note is, if you are coming at it from a fluid mechanics perspective, if you have had any introduction to a course in fluid mechanics, you might also see the same law written as tau is equal to mu times, where mu is the viscosity, du over dy, where u is the velocity. And I will leave it to you as an exercise to convince yourselves that they are all different ways of writing the same Newton's law of viscosity. So that some caveats to keep in mind before we proceed. And then we note that for the purposes of modeling, these are our elements for the modeling, the Hookean element and the Newtonian element. Because you have independent elastic and viscous components here, the responses can be described using a combination of Hooke's and Newton's laws, and we are going to look at two models, and what will distinguish one model from the other is how we combine these elements, right? And one more point to keep in mind before we move forward is we are going to take a fairly straightforward, simple approach using scalar notation. This is typically valid for 1D uniaxial, right, kind of deformations. But technically, all of this, if you look at standard textbooks, they will use tensorial notation, essentially stress, strain rate are all second order tensors. But that's a subtlety that we will not quite worry about for the purposes of this lecture, because our goal, remember, is to understand viscoelastic, linear viscoelastic modeling in the context of polymeric biomaterials, right? But again, it's one caveat that you will have to keep in mind as you look through the equations that we are going to be deriving in the rest of this lecture. So with all that being said, let's first look at the first model, which is the Maxwell model. In this model, the spring and dashpot, so this is the spring and this is the dashpot. S and D simply represent the spring and dashpot, and capital E represents the elastic modulus associated with the spring, eta represents the viscosity associated with the dashpot. These two are connected in series, and immediately based on the configuration, you will be able to appreciate that when a stress is applied, the stress is going to be the same throughout, right? So sigma sub S is the same as sigma sub D is the same as sigma, there is no difference. However, the strain, the total strain epsilon is going to be the sum of the strain in the spring and the dashpot. So epsilon is given as epsilon S plus epsilon D, or if you take the time derivative, you are going to get d epsilon over dt being equal to d epsilon sub S over dt plus d epsilon sub D over dt. And now you can ask, how do the individual elements respond? So if you take the spring element, this is simply the Hooke's law, the Hookean element. We have just added the subscript here to note that this is for the spring. So sigma is capital E times E sub S, or if you again take the time derivative, you are going to get d sigma over dt is equal to capital E times d epsilon S over dt. Essentially what we are trying to do is, we are trying to determine d epsilon over dt by individually looking at d epsilon S over dt and d epsilon D over dt. Once we get expressions for these two, we will substitute it back in this expression to get a relationship between sigma and epsilon for the entire system, right? That's where the derivation is going to go. And that's important to note for derivations, because when you start off, it's very important to have an idea of where you want to get to with the derivation. Otherwise, you're going to keep going in circles, and even if you have found what you need, you may not realize it if you don't have that intuition at the beginning to know where you want to get to, right? So that's important for us to understand. So like I just said, for the spring element, for the Hookean element, we have d sigma dt is capital E times d epsilon S over dt. And likewise for the dashpot element, this is simply the Newton's law of viscosity recast essentially for the dashpot, right? Sigma is stress is proportional to strain rate. That's essentially what this equation is saying. So now you see from these two, we have d epsilon S over dt and d epsilon D over dt, both of which can be now substituted back into this equation. And what does that give us? That's going to give us the Maxwell model. So, if you substitute for d epsilon s and d epsilon s dt and d epsilon d dt from 4 and 5 into equation 3 and you do a bit of rearranging, you will end up getting this equation, which is famously called the Maxwell model, where this eta over E, we are referring to it as the relaxation time scale or T-rel. In some textbooks, you will find the symbol tau being used. I'm avoiding using the symbol tau because again, depending on the context, it can refer to different things. So, we are explicitly using the notation T sub rel and not using tau. It's sort of ironical how we are constrained by Greek symbols. At any rate, so now what we want to do is, now that we have the model or the governing equation for the model, now we subject this model to the two types of viscoelastic behavior that we want the model to predict, namely creep and stress relaxation. So, in one case we are going to say let the strain be retained, be imposed and remain constant, and then we want to see how stress relaxes. The other case, we impose a sudden constant stress and then we ask how does the strain increase with time, right? And can the model predict these things, which closely should match what you would see in real life, at least qualitatively, for polymeric materials. So, first we will look at creep and stress relaxation, and within that we will look at creep first. So, remember, creep is the material is held to a constant stress, which means because stress is constant, d sigma dt is going to go to 0. Now, if you substitute d sigma dt going to 0 in the Maxwell equation here, you are going to get d epsilon dt is sigma naught over eta, and that is unphysical because what it is saying is rate of change of strain with time is a constant. Sigma naught is a constant, eta is a constant that only varies, eta, remember, only varies as a function of temperature, and because temperature is fixed here, and that is one of the assumptions we have implicitly made, sigma naught over eta is going to remain a constant. Now, that means that d epsilon dt is going to be a constant, right, which physically essentially means that the rate of change of strain with time is a constant, and we already know that is not true for polymers, as we have seen earlier. So, this model, the Maxwell model, predicts creep very poorly, right. That is the case for creep. Now, what about stress relaxation? So, in stress relaxation, what you do is you hold the material to a constant strain and then you track how the stress relieves, right. So, when constant strain simply means E is equal to epsilon, so d epsilon dt is going to go to 0, right. Now, if you substitute again this in the Maxwell model and you substitute eta over capital E as T relaxation and you rearrange, this is what you will get. And if you integrate that expression, you will end up getting an expression for sigma of t that shows some kind of exponential dependence, right, where sigma naught is simply the initial stress that the material experiences in response to that sudden deformation, and there seems to be some kind of exponential dependence here. So, what essentially it says is there is exponential decay in stress with time, which seems to be a reasonable prediction for stress relaxation. So, if you now subject this equation to sort of the terminal responses, so for very short times, this t tending to 0 or t relaxation tending to infinity, this model will predict that the material will behave like an elastic solid, right. And for very long times, right, very long t's or very small t relaxation times, you will end up getting viscous dominant kind of behavior, right. And that should make sense if you are now able to connect all of what I said to the idea of Deborah number that we saw in the previous lecture, namely lecture number 24. So, I will repeat that. What you are getting is for very long times or very short relaxation time scales, you are going to get predominantly viscous dominant responses, and for very short times, that is t tending to 0 or very long relaxation time scales, you end up getting dominant elastic solid like responses. Again, all of that can be contextualized in against the Deborah number, because ultimately Deborah number is simply one way to think about relaxation time scales versus an observation or an experimental time scale, right. So, essentially the Maxwell model seems to do a reasonable job, right, of predicting stress relaxation. Of course, from this you can obtain the relaxation modulus capital E of t. Now, to understand again this a bit more intuitively, we will look at this again more physically. Now, if you subject the Maxwell model to creep, which involves the application of a constant sudden stress, then you have instantaneous deformation of the spring, and then the dashpot is going to deform at a constant rate with time, right. And as long as the load is continued, deformation will continue, right. But note here that this kind of a response, right, that you see here does not accurately capture what would happen for creep in a real polymeric material. So, this is incorrect. So, you get poor prediction of creep, and again, as long as you keep applying the load, the deformation will continue forever, right. Now, that is the case for creep. Now, for stress relaxation, what you see is when instantaneous strain is applied, the spring will respond instantly and develops the stress as shown here, and then over time the dashpot starts to deform slowly, taking over the response essentially from the spring, and at some point when you are going to have the time scales, the t being equal to the t of relaxation, the stress reaches a value of 36.79% of the initial value. That just comes from substituting t is equal to TREL in the stress relaxation prediction from the Maxwell model. Essentially, this is 1 over E, that is where it comes from. And for very long times or very large times, essentially t tending to infinity, the stress essentially goes to decays to 0. Now, we say this is a reasonable approximation of stress relaxation because ultimately this is going to predict that the stress is going to decay to 0 at very long times. But while that could be true for some polymeric materials, for other polymeric materials the stress may never actually fully go to 0. You may end up having residual stress. But nevertheless, this is still a very good starting point for us to understand, at least qualitatively, that the Maxwell model, while it is a lousy predictor for creep, it's a reasonably good qualitative predictor for stress relaxation, right. That is the Maxwell model where the Hookean and the Newtonian elements are combined in series. Now, just the fact that I have said that they can be combined in series also should suggest to you that they can be combined in parallel, and that is going to lead to the other model that we are going to see, which is the Kelvin-Voigt model, also sometimes just called the Voigt model, where the spring and dashpot are connected in parallel. The same spring, same dashpot, governed by the same Hooke's law and the same Newton's law, now they are connected not in series but in parallel. And in developing the governing equation, we are going to use the same kind of arguments as we did for the Maxwell model. So, again here when stress is applied, because they are connected in parallel, you will be able to immediately appreciate from the configuration that the strain is going to be the same. Essentially, the strain epsilon is the same as the strain in the spring, is the same as the strain in the dashpot. But the stress, total stress, is going to be sum of the stress in the spring plus the stress in the dashpot. Now, again, if you look at the individual elements and how they how to think about them. For the spring element, of course, you anyway have Hooke's law, where except now we have clarifying that it is for the spring. So, sigma sub s just clarifies that it is for the spring. So, sigma sub s is equal to capital E times epsilon, and for the Dashpot element, again you have your familiar Newton's law of viscosity, which is sigma sub d is eta times d epsilon over dt. Now, all you have to do is substitute for sigma s and sigma d in equation 2. So, essentially substituting 3 and 4 in 2, and if you do a bit of rearranging, you will end up getting the expression for the Kelvin-Voigt model or the Voigt model, where again eta over E is given as T retardation, right. So, that is the expression for the Kelvin-Voigt model. Now, again we can do the same thing that we did in the Maxwell model. Subject this model to creep and stress relaxation and try to understand if the model is actually able to predict, at least qualitatively in some sense, what you would see for a polymeric system, right. So, to do that, we first look at creep, and again creep simply is the stress is held constant. So, sigma is just sigma naught. Now, if we substitute that in the Kelvin-Voigt model, you end up getting d epsilon dt is sigma naught over eta minus eta over T retardation. Essentially, this term is E epsilon over eta, eta over capital E is T retardation as defined here. So, we get this expression. Now, once you have that, you can integrate it and then you will end up getting an expression for epsilon of T, essentially how strain varies with time. And again you see this seems to predict a non-linear increase in strain with time. Now, which seems to be a reasonable prediction of creep. Essentially, at very small times, this is going to prevent that sudden jump in strain, and at very long times, you will reach some kind of a constant plateau value, right. Those would be considered what you would call the terminal responses, and that seems to be a reasonable prediction of creep, where you are not simply seeing a linear increase a jump and a linear increase in deformation as a function of time as was predicted by the Maxwell model. You are seeing some kind of increase, but in a non-linear fashion with time, right. And again from this you can obtain the creep compliance d of t. That is the case for creep. Now, for stress relaxation, what you do is you are deforming the material suddenly to a constant deformation and holding it. And so, epsilon is equal to epsilon naught, which means d epsilon over dt is going to go to 0, because epsilon is a epsilon naught is a constant. So, if you substitute that in the Kelvin-Voigt model, you are going to get stress to be predicted to be a constant value. Stress is simply elastic modulus times the constant strain value, and we know that is not physically correct, because when subjected to the stress relaxation experiment, when held at constant deformation over time, the stress is going to decrease with time, right. The material is going to relax, right. So, the Kelvin-Voigt model does a very poor job in predicting stress relaxation as a function of time. Essentially, it states that stress remains constant with time, which is incorrect. Again, that is just looking at the equations. Can we now more intuitively understand the physics of it by looking at the plots themselves? Again, just as we did with the Maxwell model. Now, if you apply creep and subject the Kelvin-Voigt model to creep, where a sudden constant stress is applied, and remember, they are connected in parallel, the spring and dashpot. Essentially, that is the main difference, right. So, you take the same spring and dashpot in both Maxwell and Kelvin-Voigt. The way they are connected makes all the difference in the responses, right. In one case, they are connected in series, in the other case, they are connected in parallel, and the relative responses are governed by the configuration itself. That is the key difference. So, that difference of series versus parallel makes all the difference to what kind of behavior the model can predict. So, you have to be able to relate the equations for the model and the predictions of stress and stress relaxation and creep from the models to the physics of the configuration itself and how the different Hookean and Newtonian elements respond in the Maxwell and the Kelvin-Voigt models. So, that connection is very important to make. So, here once the constant sudden stress is applied, the spring wants to immediately deform, but that spike that you typically see with the spring is prevented because you have this Dashpot element connected in parallel, right, which remember we did not have in the Maxwell model where they were connected in series. So, the spring could immediately instantly respond, right, and then the Dashpot will slowly respond with time. Here, because they are connected in parallel, the Dashpot element prevents that sudden spike initially. Again, as you continue to hold that constant load, the strain continues to increase, but in a non-linear fashion such as this, as opposed to a linear fashion that we saw in the Maxwell model, largely coming from the viscous element connected in series to the spring in the Maxwell model. And at very, very long times, the strain approaches a constant value. Essentially, what is happening is the strain rate continues to decrease, and at very, very, very long times, the strain rate essentially almost goes to 0, which means if the strain rate goes to 0, the viscous element does not really do much there. So, the deformation eventually plateaus off, and what you get is some kind of a constant value that is just plateauing off. So, that is a reasonable approximation of creep. We say reasonable because again this is just one way to think about creep, right. You can also have for example, this kind of a value that is plateaued off eventually could occur for say thermosets. For thermoplastics or other kinds of materials, again depending on the temperature, you can have a very, very small but yet constant increase in strain with time, even for very long times, right. So, the deformation can keep continuing, but at a very, very, very small rate without actually reaching a plateau. So, again those differences aside, we still say that the Kelvin-Voigt model is able to predict creep quite well. Now, that case is not true for stress relaxation, where we have already seen from the equation that the Kelvin-Voigt model is going to predict constant stress for a stress relaxation experiment, which is unphysical, right. So, essentially what is happening here is because you have connected them in parallel, when you want to apply an instantaneous strain in stress relaxation and hold it, that is actually physically not possible because of the Dashpot, right. And any instantaneous strain that you can possibly apply that viscous dissipation is going to occur during that loading ramp, right. And thereafter, once you hold the strain constant, right, the viscous element is not going to respond. It's essentially there is going to be no viscous flow thereafter once the strain is held constant. After that, the constant stress is held only by the spring, and you get primarily an elastic dominant or elastic only response, which is going to persist as long as the strain continues to or deformation continues to persist. Of course, all of this is incorrect or unphysical, because we know that as a function of time for a polymer under constant deformation, stress is going to relax, and the Kelvin-Voigt model is not able to predict that. So, just to summarize, the Maxwell model connects the Hookean spring element governed by Hooke's law, where stress is proportional to strain, to the Newtonian viscous element, namely the Dashpot, governed by Newton's law of viscosity, where stress is proportional to strain rate. Those two are connected in series, and the Maxwell model does a reasonably good job of predicting stress relaxation, but does a terrible job of predicting creep. Likewise, in the Kelvin-Voigt model or the Voigt model, the two elements, the Hookean element, that is the spring, and the Newtonian element, that is the Dashpot, are connected in parallel, and it turns out that the Kelvin-Voigt model does a very good job of predicting creep, at least qualitatively, and in contrast, the stress relaxation behavior is not captured at all in the Kelvin-Voigt model, right. So, one immediate question you can ask is there a model that can reasonably capture both physics? And that leads us to other advanced models, and for the purposes of this lecture, we are just going to offer some comments on what kinds of models that exist without getting into the details of them. This is just for you to get a sense that there are such models that can help predict or capture both aspects, right. One such model, which is the simplest of models, is called the standard linear solid model, right, or SLS, where you have multiple springs and dashpots in combination, right. So, it is in some sense a combination of the Maxwell and the Voigt models, and it is the simplest model for linear viscoelasticity that is able to predict both creep and stress relaxation, right. And of course, you have here both a Maxwell representation and a Voigt-Kelvin representation. Essentially, what you have here is, so for example, here you have one Maxwell arm, which is the spring and dashpot connected in series, but that entire system is now connected in parallel to another spring with E1. Essentially, the parameters in the model now are able to capture long-term elastic stiffness, one of these. The other is going to capture delayed or transient elastic stiffness, which can relax over time, and of course, the viscous element is going to capture the time scales associated with the viscoelastic responses. So, in that sense, that the standard linear solid model is able to capture reasonably well the physics of both creep and stress relaxation. And of course, there are other advanced models as well, and that has to, one such model is the generalized Maxwell model, which is used to model relaxation when you have multiple relaxation timescales, right, which is typically what will happen in a real polymeric material. The Maxwell model that we saw has only one timescale associated with it, right, only one exponent. Now, when you look at soft connective tissues and you look at viscoelasticity in them, you will end up getting a multiplicity of relaxation timescales arising due to different reasons. If you just take one example as shown here, if you just take collagen as an example, which is just one aspect of viscoelasticity in complex soft connective tissues, if you just think about the fact that the collagen fibrils and fibers have different lengths, and the shorter units contributing lesser to tissue relaxation, you end up seeing that a distribution of timescales will emerge, right. Relaxation timescales, there is a whole bunch of them, right. And while the Maxwell model that we have just seen in this lecture is not able to recapitulate a multitude of relaxation timescales, the generalized Maxwell model is able to do that, and that is used to model stress relaxation quite well in polymeric materials, particularly polymeric biomaterials, right. So, the generalized Maxwell model uses many Maxwell elements such as shown here to capture this distribution of relaxation timescales. So, you have multiple relaxation timescales and several Maxwell elements in parallel, right, such as these, as many as you want. The strain in each element is the same, the stress is the sum across all the elements, and this is used to model relaxation where you have multiple relaxation timescales. Of course, you can have a generalized Voigt-Kelvin model likewise. There are many such models, but again the goal of this lecture is to understand the physics of how linear viscoelastic models are developed and built. Again, we have looked at a very simplistic first pass kind of an understanding of these models, but the hope is you have at least now a sense of bulk responses from a viscoelasticity perspective, and then trying to capture them in the form of equations, particularly when those equations are subjected to terminal responses, you try to understand what kind of responses do you get. So, that is sort of the idea behind this lecture. So, if you can build intuition to understand the physics of some of these processes such as creep and stress relaxation, you will get a better understanding of viscoelasticity in general. And of course, these are just the standard linear solid model and the generalized Maxwell model are just to help you appreciate the complexity involved in viscoelastic modeling, right. So, that is a good segue for us to go to the last slide in this lecture, which is to understand how all of this contextualizes for polymeric biomaterials by looking at specific tissues. Here we are looking at the articular cartilage. We have already looked at tendons in an earlier lecture. Now we are focusing on the articular cartilage, and that is shown here in this picture. Now right away you see there is not just one molecule or one particular biomacromolecule that is responsible for all the properties of articular cartilage. It is a combination and a complex interplay between many of the biological macromolecules that we have seen, most importantly collagen and proteoglycans. And the structure property relationships for collagen and proteoglycans have been dealt with in very great detail in lecture 19 and 20. So, now would be a good time to pause and recall some of those concepts as we see how those structure property relationships can now influence the functionality of the articular cartilage and its eventual everyday use. So, essentially this is viscoelastic tissue that is experiencing a variety of different kinds of loads, including compression, shear and tension. And articular cartilage can creep to an equilibrium point under compression, and once the constant load is removed, that creep is mostly recoverable, and this has to do with how the water exits and enters the matrix, and that largely can be tied to the charge on the proteoglycan matrix, right. So, you see how beautifully we are now able to connect what we saw in terms of structure property relationships for charges etc. on proteoglycans now to their ability to absorb, retain or resorb water etc. And how that is related to creep and creep recovery in articular cartilage, right. And as it goes out, the viscous drag on the fluid that is extruded is the energy dissipation mechanism in the articular cartilage. And in diseases such as osteoarthritis, where the cartilage starts to degrade, this is not possible, right. Which is why for lubrication, many a time the first pass solution given is hyaluronic acid injections for such patients. But now I will leave it to you as an exercise to go back and look up what is the role of hyaluronic acid in contributing to the properties of the articular cartilage and re-lubricating it. Does it have anything to do with viscoelasticity at all? That is something that I would encourage you to go back and look up, right. Now, let us quickly look at the interplay between collagens and proteoglycans and how that contributes to both tensile strength and compressive resilience in the articular cartilage. The proteoglycans present in the articular cartilage influence the collagen mechanics indirectly. Again, you have to relate the role of proteoglycans to charges and the ability to get hydrated, right. So, charge alters the mechanical properties indirectly through similar charge-charge repulsions and for the ability for the proteoglycans to absorb a lot of water and retain it, right. That swelling pressure exerted by the proteoglycan charge density inflates the collagen network, and under tensile loads that is countered by resistance of the collagen network, right. So, collagen is excellent in tension, so the collagen is able to sustain the tensile load. Now, if you look at compressive resilience, right, it is now very well documented that compressive modulus for articular cartilage strongly correlates with the glycosaminoglycan content. Again, this is something we have seen in great detail in lecture 20 when we looked at it in the context of proteoglycans. Essentially, they are the long chain polysaccharide molecules that have a core attached to a core protein, right. As an example, we have seen that aggregan is one such molecule that binds to hyaluronin in the presence of linked proteins to form aggregates such as shown here. So, these pictures should not look unfamiliar. We have seen this in great detail in lecture 20, and of course, this is the collagen itself, right. So, aggrecan is the proteoglycan, and you can think of the GAGs being chondroitin and keratin sulfate, and there is some kind of a macromolecular assembly that happens because of aggrecan binding to hyaluronin in the presence of a linked protein to form these aggregates. So, this would be what you would call macromolecular assembly, the formation of these aggregates. And of course, the sulfates and the chondroitin sulfate in aggrecan are tightly packed and highly charged, and so the aggregates can now imbibe water. That leads to cartilage having resilience to compression, right. So, again when cartilage gets lost or eroded with time due to osteoarthritis, you can now start to see what kind of adverse effects it will have on the patient in terms particularly of the compressive resilience, right. So, like I have said, this is a fairly complex topic, and modeling the viscoelastic responses in such complex tissues is actually a topic in itself, it is a research area by itself. What we have done in this lecture is just maybe not even to scratch the very top layer of this topic, but the hope is you get a good sense at least of the motivation for studying such topics, and appreciating again why looking at this in the context of polymeric biomaterials is important, because any biomaterial that you are now thinking of to mimic the properties of some of these complex biological soft connective tissues, you can now start to ask from a design perspective, what kind of structure property relationship should I kind of engineer into the material such that I can get some of these very advanced kind of responses that, again, remember, does not arise from a single molecule. It is a complex interplay between multiple molecules. So, are there aspects beyond just one molecule structure property relationship that need to be considered for designing materials that can recapitulate at least some aspects of the complex viscoelastic responses that these kinds of tissues end up showing. So, with that, we will end this lecture.